Okay. So any questions? First of all, do you want me to repeat anything that we had discussed in the lectures?
Şu baştaki Day2 step function'ı nasıl yapıyorsunuz? Onlar step function'ı.
Now, the question is this one. We have this function. We call it the step function. And we define it. It is 1 if its argument is larger than 0. And it is 0 if its argument is less than 0. So basically, if you would plot it as a function of x, this is x is equal to 0. For x less than 0, it is 0. For x larger than 0, it is 1. It just looks like a step, so that's why we call it the step function. And the question asks to us to show that the derivative of the step function with respect to x is just our Dirac delta function. This is what we need to prove. Well, let's see. What are the properties of the Dirac delta function? So we have to prove that the derivative of the step function satisfies all the properties of the Dirac delta function. So what are the properties? Well, I mean, infinite is not really a value. So what we know about the step function, it is 0 except on one point. So that is one property of the Dirac delta function. The Dirac delta function is 0 everywhere except on a single point. Well, we as physicists, we say that, okay, its value at that point is infinite, but infinite is not really a value. So I would rather avoid that. I mean, we are physicists, we are kind of relaxed about these mathematical formalities, but nevertheless, let's avoid calling infinite a number or a value. So it should be 0 everywhere except on a single point. Well, let's look at this step function. Its derivative. What is the derivative if x is larger than 0? 0, because the step function has, if x is larger than 0, the step function always has the value 1, which is constant. Derivative is 0. What is its value if x is less than 0? Again, the same argument. It has, for x less than 0, it is just a constant. It is a constant value, so its derivative is 0. So at least the derivative of the step function satisfies one of the properties of the Dirac delta function. Now we need a second property. What is the second property of the Dirac delta function? Its integral should be 1. Well, we can say that its integral over all x should be 1, or we can say that its integral around from a point below 0 to a point above 0 should be 1. Well, they are the same because it's almost everywhere 0 anyway. So let's look at the value of the integral of the step function as a function of x from, let's say, from the left of 0 to the right of 0. We already know that this is equal to from minus infinity to infinity of the theta by dx times dx. Because from the left of 0 up to minus infinity, the step function, the derivative is 0. From the right of 0 up to infinity, its value is again 0. So just extending these limits to minus infinity and plus infinity doesn't change its value. And this is equal to, well, we are talking about the integral of a derivative of a function, but that is nothing but the difference of the values of the function at the two limits. Right? So this is the value of theta at the point 0 plus minus the value of theta at the point 0 minus. What's the value of theta at 0 plus? To the right of 0 for values larger than 0. Its value is 1. To the left of 0, what's its value? 0. So this is 1, this is 0, So this is equal to 1. So basically, that means that the integral of the step function over 0 is 1. So it's this weird function that is 0 almost everywhere except on one point, but its integral is 1. But these are the properties of the Dirac delta function. So we define the Dirac delta function to be the function that is 0 almost everywhere except on a single point, and its integral is 1. So basically this is our proof. So just combining these two, that its derivative, the derivative of the theta function is 0 almost everywhere except on a single point, plus its integral is 1, tells us that the derivative of the step function is actually the Dirac delta function. So this is our proof. So you seem to be having problems with the Dirac delta function. So we can do a bit examples of the uses of applications of the Dirac delta functions after you finish your questions. So any other questions? Anything you want repeated?
Neden eksi bu son sonrası kullanıyoruz? Yani sıfırla minus sıfır işte pozitif değil. Hani Dirac delta 1'e eşit derken. Yani Dirac delta fonksiyonunun işte integrali 1'e eşit ama neden hani hep eksi sonsuzla son sonrası yazılmış?
Well, you see, because it is 0 everywhere. Maybe possibly at a single point. I mean, it doesn't make any difference whether we write it from minus infinity to infinity, or from 0 minus to 0 plus, or from minus 1 to plus 1. It doesn't make any difference. Because it is, I mean, the difference in between these two integrals are the contributions from regions where our function is exactly 0. And hence there is no contribution from that. I mean, it's just a matter of taste. I mean, you will see that in some books, in the definition of the Dirac delta, once they state that it is 0 almost everywhere except on a single point, then they write this one. In some other books, you will see that they first say that it is 0 almost everywhere except on a single point, and then they write this one. They mean the same thing, since our function is 0 everywhere, almost.
Step function'ın sağlam ve soldan integral olduklarını yaşıyor. Yani sağdan yaklaştıkça soldan yaklaştıkça sıfırdayken oluyor.
Well, usually you don't define this value of the step function at 0. It depends on, I mean, you see, step function, in a sense, is not such a nice function because in physics, all the functions we have are smooth, integrable, etc. Step function is not. So that's why we don't like it that much. And the value at 0, I mean, depending on in which case you are using it, you will need to take the value at 0 to be 0 or 1. Most frequently, you will see that it is taken to be 1/2. But you should better, your result or your predictions, let's say, should better not depend so precisely on how you define your step function. Well, you see, we will do some examples. I mean, whenever you want to write something that is 0 in one region and non-zero on the other region, well, step function is there for you. It just sets the value of a given expression to 0 in a certain region. That's where we will be using it. For example, if you remember the exercise that we did in the lecture. Yes. So we had this wire, which we said that has a length L, total charge Q. And then we had chosen our coordinate axis, origin to be at the center of the wire. This is X, this is Y, this is Z. And we were looking for the charge density. Now, what do we know about the charge density? This is equal to 0. 0 if X is not equal to 0. or x might be 0, but y is not equal to 0, or z is larger than L over 2, or z is less than minus L over 2. Under all these conditions, rho is 0. So to impose these conditions for this criteria, z is larger than L over 2 or z is less than minus L over 2, what we can say is rho of r, let's say, is proportional to. So we need to put a function, I want to put a function over here that is 0 if z is larger than L over 2. But I know already such a function. If z is larger than L over 2, this function is 0. And I want to put another function that will be 0 if z is less than minus L over 2. And I also know that function. It is proportional to that one. I don't know the proportionality constant, I didn't write it down, but at least I know that if z is, this function over here is 0 if z is larger than L over 2 and 0 if z is less than minus L over 2. So at least whatever comes here, it doesn't need to satisfy these two because this function already satisfies these two. And what we had done was well, it should be 0 if x is not 0. So we already have a function that satisfies that property, the Dirac delta x. It should be 0 if y is non-zero. So we already have a function that satisfies it. So rho is non-zero only if x is 0, y is 0, and z is in between L over 2 and minus L over 2. So the proportionality over here can be, in fact, any function that you like. It doesn't have, I mean, we assumed it to be a constant, but it doesn't have to be a constant. But since x has to be 0, it cannot depend on x. And y has to be 0. We cannot really write the y dependence. So here we can put, in fact, any function that depends on z. So if you have a charged rod, it is charge density has this, should have this form. These functions over here make sure that it is 0 everywhere except on this rod. What is its value on the rod? Well, we don't know yet. We have to evaluate it. We need more information. Well, one information that we might be given is that the charge is uniformly distributed over the rod. So that can be one information that we have. Well, if we are given that the charge is uniformly distributed over the rod, whether we are on this point or on this point, the charge density has to be the same. Well, that basically tells us that this function f cannot depend on z. Just by knowing the shape of our object, we can only say these functions. Well, the proportionality constant, well, in fact, it can depend on x, y, or z, but if x is non-zero, this is already 0, so it doesn't really make any sense to call this a dependence on x. Now, do you see why we have these step functions here? Well, in the lecture, instead of writing theta L over 2 minus z, theta L over 2 plus z, I had written theta L squared over 4 minus z squared. Now, because if z is larger than L over 2 or z is less than minus L over 2, this z squared is larger than L squared over 4. This is negative, so this is 0, the right-hand side. If you look at the left-hand side, if z is larger than L over 2, this is 0. If z is less than L over 2, this is 0. If z is in between, in that case, this is 1, this is 1. So for all possible values of z, whether between minus L over 2 or L over 2 or outside of this region, the left-hand side and the right-hand side have the same values. So these two functions are equal. For example, in a given question, you might be told that the charge density increases linearly as you go away from the center of the road. That's also possible. That would just tell me that this Fz is not a constant, but it's a linear function of z. It will depend on your circumstances, on the problem that you are studying. As long as this rod is given, these functions are already given, but this will depend on how the charge is distributed over the rod. Is it uniform? Is it larger towards the endpoints, or is it largest in the middle and goes to 0 towards the ends, etc.? Well, let's see. The question is this one. This is your question, right? Let's see if both sides satisfy this, have the same values everywhere, have the same properties. If x is non-zero and y is non-zero, both are non-zero, the left-hand side is? The left-hand side is 0. The right-hand side? X and y, they are both non-zero, so their product is non-zero. So both sides are 0. If x is 0, y non-zero, the left-hand side is? Well, kind of problematic. X is 0, y is non-zero. The y, Dirac delta y is 0. The other Dirac delta is, well, infinite, basically. So we have the 0 times infinity, which seems to be uncertain. But nevertheless, in this case, it is 0. Both sides are 0. So at least both sides are 0 at the same points. Now we have one more property that we need to satisfy. The left-hand side, if you integrate over dx dy, from minus infinity to infinity, this is equal to 1. You can just integrate 1. The integral over y just gives you 1. The integral over x gives you 1. So it's just 1. If you go to the other side, from minus infinity to infinity dx, minus infinity to infinity dy, Dirac delta xy. Well, let's first make a change of variables in the y integration. Now let's call u is equal to x times y. I'm doing the y integration only. So the y integral is inside the x integral. In the y integration, x is just a constant. So u is equal to x times y. Y is equal to u over x. dy is equal to du over x. So that integral is equal to from minus infinity to infinity of dx, from minus infinity to infinity of du over x times Dirac delta of u. Well, the u integral just gives me 1. What is left is from minus infinity to infinity dx over x. This is not defined. So this is not necessarily true. Now this integral, the problem is the point x is equal to 0 is problematic over here. Depending on how you define this integral can be 0. Most of the time it is defined to be 0, or it can have any value that you like, in fact. But definitely it doesn't need to be 1. We don't know. I mean, what your friend asked whether this product is equal to this one. That is your friend's question. Well, if these two sides were equal, they should have the same properties. They should be, well, since we are talking about the Dirac delta, they should be 0 at the same points. And whatever integral you consider, the integral of this one should be equal to the integral of this one. Otherwise, they won't be equal functions. Well, let me also write it in this way. Here, I'm not really multiplying the arguments to write this equality. I'm just checking the value of the left-hand side and the value of the right-hand side at every point. Now, if you check the value of this function and the value of this function at every point, they have the same value. Then I can say that they are the same functions. Although they look different, they are basically the same function. I'm not multiplying the arguments. I could have also said that, well, let me write here, theta of L over 2 minus z theta of L over 2 plus z. This is equal to theta of L over 2 minus z divided by L over 2 plus z. This is also true. Since the step function only depends on the sign of a function, not its value. Sign of its argument, not its value. You can do whatever you like, actually, with the argument, as long as you are not changing its sign. And there are many operations that don't change the sign of a number, but change its value. Like taking the 1 over a number that doesn't change the sign, but it changes the value. For example. Well, you see, the step function, this is the definition of the step function, whatever the argument is. As long as the argument is positive, it is 1. If the argument is negative, it is 0. Well, the argument can be just x, or it can be a complicated function of x, y, z, or I don't know how many variables you would like to put in. Just whatever the argument is, it can depend on any other parameters. Whatever the value of the argument is, if it is positive, step function is 1. If it is negative, step function is 0. For example, this is not true. Again, to test it, you just check the properties of both sides, its values at both sides. So you can have, for example, x and y, they can be both positive. In that case, x, y is positive. So the step functions here is 1. The step function here is 1. It seems to hold. But if you take x to be negative, y to be positive, or the other way around, well, one of the step functions on the left-hand side is 0. So the left-hand side is 0. X times y is negative since 1 is positive, the other one is negative. So this is negative, step function is 0. It still seems to hold. But if x and y, they are both negative, both step functions over here are 0. But if x and y, they are both negative, their product is positive. Since their product is positive, this step function is 1. So there's no equality between the left-hand side and the right-hand side. There is not really a relation between the product of two step functions and another step function, not a general property. But in certain special cases, by just comparing the values of both sides, you can say that you can convert the product of two step functions into another step function. Other questions? Let's assume we have a ring on the xy plane of radius r, total charge q. What is the charge density? This is a ring, by the way, not a disk. Inside is empty. And remember, Q is equal to d cubed r rho of r.
R d phi times dr.
R d phi times dr.
Şunu buna oynayacağız hocam. Bunun integre edilmiş hali sıfırdan 2pi'ye kadar.
D phi, integrating d phi from 0 to 2 pi, and what about dr? You see, outside of integral, dr will be 0.
Hocam ring olduğu için 0 to r diyemiyoruz. Ya disk olsa diyebilirdik de.
We will do the disk next. What do we know about the density, charge density, without writing the expression? What can you say?
Yük bölü alan diyeceğiz.
No, I mean, for this case, for this special, where is it 0? Everywhere except on the ring. So it is for 0 if z is non-zero, if x squared plus y squared is not equal to r squared. So it's basically at very few regions it is non-zero. We can choose to use Cartesian coordinates or cylindrical coordinates. I would rather switch to cylindrical coordinates if you don't mind. Are you familiar with cylindrical coordinates? Rho is not equal to r. So already we know that it is there almost everywhere. I mean, the region that it has rho non-zero doesn't have any volume. Its volume is 0. Since we are talking about the volume density, volume charge density, which is concentrated in a region with volume 0, its value on that region should also be infinite. Because as you pointed out, the charge density multiplied by the volume should give us the total charge. But the volume is 0, So the charge density should be infinite. So we have this weird function who is 0 almost everywhere except in a region of volume 0. Well, that is the Dirac delta function. So rho of R will be equal to, well, there is a Dirac delta of Z, because we know that if Z is non-zero, then the Dirac delta function, then the charge density is 0 anyway. Then we have the Dirac delta of rho minus R. Because if rho is not equal to R, it is 0. Why? Which row and which row it looks similar? I mean, I have a single row. Oh, that row. Okay, okay. You're right. What shall we call it? Small r. But this time r is equal to square root of x squared plus y squared. It's the cylindrical coordinate r, not the distance from the origin. And basically, these two make sure that our density of states is 0 everywhere where it should be 0. And of course, we can have a function multiplying these Dirac deltas, which can, well, the only parameter left is the angle phi. If we have a ring, this is the most general form of the charge density.
Peki hocam, şuradaki gibi diyemez miydik? R d phi dr, phi sıfırdan 2 pi'ye, diğer içinde işte R'dan R artı işte.
Let's see. R d phi dr, phi goes from 0 to 2 pi, and dr goes from?
Çok ince bir kalınlık işte, yüzük kalınlığına kadar bir şey.
It is 0. The thickness of this ring is 0.
Ama
But
bu sefer diğer tarafta da hocam yük yoğunluğu sonsuza gidecek. Çok ince.
sure, it should be. You see, just think of it, I mean, okay, it will be a bad analogy, but think of it as a black hole. The density goes to infinity. Well, of course, this is an idealization. Your friend has a point. I mean, in real life, we don't have these infinitely thin rings. But I'm not so sure you would be happy trying to write down the density of states of that ring. We will do the disk, for example. Then we can discuss your claim. Okay, so now we need to determine this F. What should be this F? Okay, what do we know about the charge distribution? Well, except that it's on the ring. We are not yet given anything, but let's assume that it is uniform. So the charge is uniformly distributed. It just tells me that F is independent of phi. Let's just call that constant A. So now we have our expression for the charge density. We have one more condition that would allow us to determine this value of A. We are given that the total charge of the ring is equal to, which can be written as the integral of rho over the whole volume. Well, the volume element in cylindrical coordinates would be r dr d phi dz. Rho is A times Dirac delta z, Dirac delta small r minus the capital R. Now I can carry out the, let's say the z integral just gives me 1 using the Dirac delta. Similarly, the r integral gives me capital R using the Dirac delta. Phi integral just gives me 2 pi, nothing depends on phi. So this just turns out to be 2 pi from the phi integral, capital R from the r integral, z integral gives me 1 and times A. So A is equal to Q over 2 pi r. This is the linear charge density. 2 pi r is the circumference of my ring. Q is the total charge. So this is the linear charge density. This is the charge per unit length of the ring. And now we have the charge density. Or you can also write this in this form. Well, I can convert the capital R into small r because of this Dirac delta. So Dirac delta essentially has a meaning only inside integrals, basically. And as long as it is inside an integral, Dirac delta just tells me if we are integrating over small r, Dirac delta tells me that instead of the small r, I should put a capital R. So the integral of this function and the integral of this function, they will be the same all the time. So those functions are the same. Okay, the volume element. Okay, so first, let me just clarify some notation. The volume element, you will sometimes see this notation. Sometimes you will see d cubed x. Sometimes you will see d cubed r. They all denote the volume element. Now, we are looking at the volume charge density. Okay, it is infinitely thin. That basically tells me that the volume charge density is 0 everywhere except that on the ring. And since we are looking at the volume charge density, the volume charge density on the ring is infinite. But we are always talking about the volume charge density. So that is why I have the d cubed x over here. Rho I will use to denote the volume charge density. If you remember, we defined rho as we imagined a very small volume around the point R, and we measured the charge in that volume, and eventually we took the limit that the volume goes to 0. For a point charge also, for example, the charge density at the position of the point charge is infinite. Because no matter how small the volume you take, the point charge is inside it. All of it is inside it. So the charge inside this very small volume will be constant, independent of the volume. But we are dividing it by the volume, which we take the 0 limit. So for a point charge at the position of the point, the charge density is infinite, just like in this ring. At the positions of the charges, the charge density is infinite. So that the volume integral, which will give me the total charge, gives me a finite number.
Nokta olunca infinite çıkıyor charge density. Sıfır olması için ne olması gerekiyor?
Well, at everywhere other than the point charge, it's 0. There's no charge there. So the charge in my volume is 0. I divide it by the volume. I get 0 for a point charge. So for a point charge, the charge density will be 0 everywhere except at the position of the point. Now let's do the disk. Well, let's also imagine not a very thin disk, but a disk with some thickness. Here, everything will be finite. let's say it has a thickness D, radius R, total charge Q, and if you would just plot it from straight on the side, Y and Z, this is how the disk looks like. So the bottom is on the XY plane. At Z is equal to 0, the top is at Z is equal to D. So what is the charge density?
Q bölü R dr d phi dz.
Okay, so your claim, Q over R dr d phi dz. This is rho of R.
Tabii integral içerisinde.
Tell me the integrals, dr, the limits.
Sıfırdan R'ye kadar.
Okay, from 0 to R.
Sıfırdan 2P'ye kadar. Sıfırdan D'ye kadar.
So let us evaluate those integrals. We have R times dr integral gives me R. Then the phi integral gives me 2 pi. Z integral gives me D. So this is equal to Q over 2 times pi R squared times D, Q over 2V. V being the volume of my disk. This is your claim, right? This is the charge density at the position R. Do you agree?
Bir yerde hata var mı ya? Söylediğim şeyden.
So you are saying that the volume charge density is constant everywhere. That is your claim.
Yani disk içerisinde constant değil mi?
Okay, hold on. So if you are saying that if it is constant in the disk, you should reflect it somehow in your expression. You said that rho of R is equal to this one, which is just a constant everywhere. Now, how do you say that this is equal to this one in the disk? Okay, let's write it. What kind of step functions you want to put? D minus C. Okay. If Z is larger than D, then this is 0. If small r is larger than capital R, this will be 0. Anything else? So what if, for example, Z is minus 5 meters? So Z is negative, D is positive, so this is 1. If you are along the Z-axis, this is also 1, R is 0. So when Z is equal to minus 5, if these are the only step functions, in that case we have a non-zero charge density here. There is just one more step function. You see, we have the charge density should be 0 if Z is larger than D. So it is this step function over here. It should be 0 if Z is less than 0. That is the other step function we need to add. So these two make sure that the density of states is 0 if Z is less than 0 or Z is larger than D. This makes sure that if density of states is 0 if R is larger than R. So it is only non-zero within our volume. And your claim is that this rho should be equal to Q over 2V. This is your claim, right? Is it? Or
Hocam normalde basit olarak düşündüğümde pi ile kare çarpı d olacak ya hacim. Burada niye 2 çıktı? Orada biraz karıştı.
I don't know, that's your definition. You told me that it's Q over these integrals. I said fine, so I wrote it down. And it turned out to have that factor too.
Ben bunu beğenmedim. Bir yerde Dirac delta olsun diyorum.
Well, you see, we have these Dirac deltas in volume density if the charge is non-zero only in a region which has 0 volume. Because we had this point charge has 0 volume, so, but still we have a total charge. So if we want to write down a charge density for an object that has 0 volume, its charge density has to be Dirac delta, so that the integral will be finite. We consider this ring, very thin ring. Still it has 0 volume. Since it has 0 volume, its charge density on this ring should diverge, and it should be 0 everywhere else. So that's again the Dirac delta. But here we have this disk. We can, but what's the point? Each one of that infinitesimal thin rings has 0 charge and 0 volume, such that the ratio will be finite. We will not be summing anything yet. We are not calculating the total charge, etc. We are looking at a local property now, the charge density. So let's forget this one for the time being. Let's not just add dRs, dphis, and dzs as we please. We know that rho of r, as your friend has pointed out, it has to be proportional to these things. And of course, the proportionality constant can depend on z, can depend on r, can depend on phi. We don't yet know its value, but let's, for simplicity, assume the charge is uniformly distributed. Over the disk. Well, this basically tells me that this function f is a constant. Let's call it a. Then rho of r should be a times theta of z, theta of d minus z, theta of r minus r, for some value of a. We still need to relate this a to the other parameters in our problem, like we know the thickness of the disk, we know the radius of the disk, we know the total charge of the disk. And the relation is the total charge of the disk has to be equal to the volume integral of the charge density. This is how we define the charge density. If you have the charge density, multiply it by a very small volume and sum over all such small bits, the total charge is equal to Q. Well, we can still use the cylindrical coordinates. That would make our life easier. Let's say in spherical coordinates, dV is r dr from 0 to r. Well, let's go back to your integral. It's not just r, it's r dr. And then we have d phi from 0 to 2 pi and dz. Well, okay, let me just make one correction. This is not from 0 to r, this is from 0 to infinity. And z goes from minus infinity to infinity for the time being. Of rho of r, which is a times theta of z, theta of d minus z, theta of r minus r. Now I have this step function over here which tells me that if small r is larger than large r, the integrand is 0. So the only contribution comes from the region that small r is from 0 to capital R. R dr. Well, there is no limit on phi. There is no step function that contains the phi. If we didn't have a ring but a piece of an arc, for example, that would restrict the value of phi. But in our case, we have a disk, not just a segment of this disk. So phi is not restricted. Phi integral just gives me 2 pi. And the z integral, I have these two step functions, which tells me that if z is not between 0 and d, the integrand is 0. So over all these possible values of z, the only contribution comes from when z is between 0 and d, a. Now we can evaluate these integrals. The r integral will just give me r squared over 2 times 2 pi times d times a. 2's cancel, so a is equal to q over pi r squared times d. And so rho of r is equal to q over pi r squared times d, theta of z, theta of d minus z, theta of r minus r. Here, yes. No, you see, I'm using this relation. So q is equal to this integral. This integral can be written like this. And so the step functions change the limits of integrations. So I obtain this expression for the integral, and that tells me that a is equal to this one. I evaluated a. The density of states we had written already over here. The density of states is a times these step functions. So I substitute the value of a back in the definition of the charge density, and this is what I get. You see, there are no Dirac deltas over here, almost. Well, let's do one more thing, and then let's give a break. Now, we said that there's no Dirac deltas over here because the disk has a finite volume. So since it has a finite volume, the charge density everywhere should be finite. Finite times finite charge density of states times finite volume gives me a total charge non-zero. If the volume were equal to 0, then the density of states should contain some Dirac deltas, 1, 2, or 3, some Dirac deltas, and so that the 0 volume times a Dirac delta would give me a finite total charge. Now let's consider the limit when the thickness of this disk is 0. Well, in real life, of course, none of the physical disks will have 0 volume, 0 thickness, but nevertheless, that will be a good enough approximation for most of our problems, in certain cases, let's say. A very thin disk, you can just ignore its thickness. Now, let's look at, to see what the density of states become when these goes to 0, let's look at the z dependence of this function, of the density of states. So let's just have, it depends on theta z, theta of d minus z divided by d. Let's look at this function. If z is less than 0, it is 0. So here it is 0. If z is larger than d, it is again 0. In between, its value is 1 over d. Let's look at its integral over z. From minus infinity to infinity. What is its integral? That's the area below this curve. It's just 1, independent of d. Now, when we take the limit that d goes to 0, we will be considering very thin disk. If d goes to 0, then this function becomes a function that is 0 almost everywhere, except then possibly a single point, at which point its value diverges. But it diverges in such a way that its integral is always 1, whatever the value of d is. But that is how we define the Dirac delta function. This is an alternative definition of the Dirac delta function. So limit as d goes to 0 of theta of z, theta of d minus z, divided by d. This is equal to the Dirac delta of z. So infinitely thin disk rho of r will be limit as d goes to 0 of q over pi r squared times theta of z, theta of d minus z divided by d times theta of r minus r. So this becomes q over pi r squared times Dirac delta of z, theta of r minus r. Well, we could have obtained it starting from a thin disk by just noting that if we have an infinitely thin disk, the charge density should be 0 if we are far away from the disk, and it is 0 if z is not equal to 0. Since its volume is in z, it is 0. That's why we have this Dirac delta over here. It should be 0 everywhere except on a single point. And we have this step function to make sure that it is only non-zero if we are sufficiently close to the z-axis on the z equal to 0 plane. And there's a proportionality constant. We have constant or function which we have to determine by the other conditions given in the problem. In this case, we are given a disk that has a charge that is uniformly distributed. So that is why we know that this function is constant. It doesn't depend on the small r, and it doesn't depend on phi if we are given that it is uniformly distributed. And then the condition that the total charge should be equal to q would allow us to determine this factor over here, this constant factor. But again, you see, one problem, for example, in first year courses, for every possible question, we were trying to come up with a clever trick that will allow us to solve the problem. Now, our purpose now this year is, okay, we will not be trying to find tricks. We are just trying to find a general strategy that we will be able to apply to almost everything. So if you have followed in all these examples, it's a ring. We first identify the points at which we have a zero. We have our density of states is 0. If it's a range of values, then we have this step function. If it is just if it's a range of values for which the density of states is non-zero, then we had the step function. If it's just a single value at which it is non-zero and it's 0 everywhere else, then we had the Dirac delta function. And then we just multiply the step functions and the Dirac delta functions, which made sure that we satisfy those criteria. And then, of course, there's still this unknown function, and this unknown function we try to determine by using the other information given in the problem. For example, if we are we given a uniform charge distribution? Or if it is not uniform, how not uniform? We have to be given that information. If it is uniform, or whatever other information we have in the question, we can write down the most general form for this function, which will depend on certain parameters. Like if it is uniform, it will be just a constant which we need to determine, and that constant we can determine by requiring that the charge density, the total charge which is given by the integral of the charge density, is equal to the total charge of the object. So in all these examples, the steps we carried out are identically the same. Any questions?
Sorayım mı hocam? Şimdi bunu kullanarak elektrik fieldi yaratacağız ya hocam. Ona da gelip integral alacağız. Onu bu Dirac deltalar gider değil mi?
Yes. They will. I mean, if you don't have any other questions in the next hour, I will start from these charge densities that we obtain. From that, we can obtain the electric fields, as you pointed out. That we will calculate. Okay, let's give a 10-minute break, and let's meet at 9:50.